Suppose we have some matrix A, which is a data matrix, and this matrix consists of two features and three observations, where features are columns and observations are rows. So every feature is an axis on the plane, and every row is a point on that plane. And SVD rewrites this data matrix using three different matrices. And the purpose is following: we just want to find some important patterns hidden in the matrix. The matrix V tells us the feature directions. Matrix sigma describes how strong each direction is. And the last one, matrix U, tells us how each observation uses them. So the problem is that our data, pattern of our data, doesn't follow either axis, as you can see, but it follows some diagonal direction. And we want to find some vector. Let's take some unit direction. V, which is unit vector, means its length is equal to 1. And this vector is a linear combination of two features, meaning we just take some part of the first feature and some part of the second, and it creates a new vector, new direction. But we don't know which direction describes the pattern in the best way, so SVD calculates it from the values inside the data matrix. And to do that, we need to take some candidate direction and multiply it with our matrix. And it gives us new column vector where each row is projection of that observation to the direction vector. It looks like that. We just take some data point and multiply it with our vector, and we're gonna have the number which is the coordinate of that data point along this candidate direction. And we do that for every observation. That's why we need matrix multiplication. And different candidate gives different scores, so we need to somehow understand which candidate vector is the best one. And the answer is easy. We just need to calculate the magnitude of that vector. And as we know, this magnitude is just square root of sum of squared components of the vector. To move forward, we need to square this magnitude and remove the square root. We will see the reason a little bit later. And when we do this squaring, we know the property that the sum of squares components can be written as a product of two vectors. If we multiply the same vector row and with the same vector column, we're going to have the sum of squares. And now we can take our magnitude squared equation and substitute it to the form we just derived. So it looks like that. And now we can check it on our data, and as you can see, it's the same. So we're gonna score each candidate vector, each direction with this magnitude squared value. So we can define as the first direction V1 as the largest squared magnitude over every unit direction. And this V1 component is called the first right singular vector. So we can run the search, just rotating the unit direction vector and collecting the squared magnitude for each direction. And then we just select the peak magnitude value, and the angle at that value is our direction. But there are infinitely many unit directions, but we need an exact answer. So the search becomes an eigenvector problem, meaning that we can rewrite our derived formula in following way as eigenvector problem. It's okay if you don't understand it right now, I will explain it in a few seconds. V1 is the eigenvector of A transpose times A matrix we derived before with the largest eigenvalue. Therefore, the main recipe is to form that matrix, compute its eigenvalues and eigenvectors, sort them by eigenvalue where the largest one is first, and then we just read the directions, because after the sorting, the largest eigenvalue corresponds to the best eigenvector. But how are eigenvalues calculated? So let me recall you that an eigenvector is just a non-zero vector whose direction is unchanged by some transformation. Meaning, if we have some vector and we multiply this vector with some matrix, this multiplication is not gonna rotate the vector. It can only flip the direction or stretch the vector. So now we can move the right part of this equation to the left, and we got the following equation. And if we need to subtract something from matrix B, we need to have the same shape. And that's why we multiply the sigma value by identity matrix. After that, we're going to have an equation like that. And as you can see, when v is equal to 0, we have the solution, but this solution tells nothing. We need a solution which is not 0, and that's why we need to take the determinant of that equation. And it creates something called characteristic equation. So let's take a small example. First of all, we calculate the desired matrix and create the equation as discussed, and after that take the determinant. And now we can clearly see solutions which are 4 and 1, and there are eigenvalues. And we sort them, so the largest eigenvalue is first. After that, when we have eigenvalue, we need to find the eigenvector. To do that, we know that the eigenvector for two-dimensional quality has two components, x and y, and we just substitute the eigenvalues in the equation we had before instead of lambda, so it looks like that, and just solve it. And for the first eigenvalue, we have one equation where the x component is equal to 0 and y component is 3, so we can select any, like 1, which creates unit vector. And we do the same for the second eigenvalue. So in result, we have two eigenvectors. Let's do the same procedure on our data matrix, and it looks like that. So as you can see, we have two solutions, 42 and 2, and there are our eigenvalues. And now we find eigenvectors in the same way. So the eigenvector belonging to the first eigenvalue is derived as following, where we just take any number instead of x component, substitute it to the y component. So for example, we take x component equal to 4, and therefore we have the eigenvector 4, 3, with the length equal to 5. And after that, we need to have unit vector. We divide this eigenvector with its length. So the first vector looks like that. And we do the same for the second eigenvalue. So in results for two-dimensional plot, we got two eigenvalues, which describes our data in the best way. But what does the eigenvalue actually measure? So if we move back to the eigenvector equation we had before and multiply both sides on the left by the transpose eigenvector, we're going to have the following equation. And for unit vector, it looks like that. And as you can see, it's the same as the squared magnitude of this vector. So the eigenvalue is just the total squared magnitude of the data along that direction. And there is important rule: the next direction must be perpendicular to the previous one. And there is a reason for that. If we run the same search a second time, we're gonna have the same result. Nothing's gonna be changed. And we need to find another vector which describes something the previous one does not. And that's why we use perpendicular vector, because it's the direction which previous one doesn't use. And with more features, the same rules just simply continues, where the second vector is perpendicular to the previous one, and it's the second strongest component which left after the first one. And for the third, it's the same. It's vector perpendicular to the first and second vectors, and it's the third strongest direction remained after the second. But we never have to run that search repeatedly for every eigenvector, because the matrix we created is symmetric and its eigenvectors are already perpendicular and have a unit length. So when we do solutions as shown before, we already have sorted eigenvalues and their eigenvectors. And we just need to take all these directions and store them as the columns of the matrix V. Before that, we have feature 1 and feature 2, which are only described our data. But now we found new two directions, new two axes, which describes our data better. So let's move a little bit back. So as I said, eigenvalue is equal to the squared magnitude. And therefore, if we take square root of the eigenvalue, we're going to have just the magnitude. And that's actually what our components of the second matrix sigma are. And they are called singular values. So these singular values are stored on the diagonal of sigma matrix. And each value is bigger or equal to the next one. And they are sorted so the largest is first. And as I said, each singular value is just a square root of eigenvalue, which is just the magnitude for that direction. And the larger singular value is, the stronger pattern in the matrix we have for that direction. So let's look in some extreme case. Suppose every observation happened to lie exactly on the first line V1, and in result, every projection is 0 onto the second vector, and it creates singular value equal to 0 as well. That means that our data never uses this direction. So as I said, the singular value is equal to the magnitude of that direction. Therefore, when we divide this vector with its magnitude, which is its length, we obtain the element of U matrix. So it's actually just normalization, where we just divide a vector by its own length. So it creates the new vector U with the same shape, but with the unit length. But why do we need this component at all? So the idea is that the U is normalized curve vector across all observations. So vector V says which combination of features the pattern is. So it's working with columns. But vector U says how the pattern is spread across the rows, the observations. And if we have 3 observations, 3 rows in our data matrix, and vector U is equal to something like that, it means that observation 3 carries this pattern most strongly in that direction. And after that, we just collect the patterns as the columns of matrix U, like that. To summarize, matrix V tells us what is the pattern across the features. Matrix sigma tells us how strong is that pattern, and matrix U tells us how it's spread across the observations, not the columns, but the rows. So we can consider one component which looks like that. And as I said, V is a pattern across the columns, across the features. U is a pattern across the rows or observations. And sigma is just overall strength of that pattern. But one component is not enough. If we have one component, it shows one pattern, one structure. And when we add another one, we discover another pattern, another structure. So that's why we add all the components up. And all the sum can be written compactly with 3 matrices, like that. And SVD has a lot of applications. Most common are compression, where we keep only the strongest components, noise reduction, when we drop the smallest noise, and dimensionality reduction, when we find few dominant directions instead of all. So let's take a close look into compression. So imagine some grayscale image. This image is a matrix, and every entry, every element of this image is 1 pixel intensity. For example, a Taran plus sign is a matrix like that. And we can represent this image using SVD, and we do that in exactly the way we discussed. So the right singular vectors come from the eigenvectors. They are ordered from strongest to weakest. Then we calculate the singular values as a square root of eigenvalues, and so on. And this let us write the image as the sum of simpler images, where each term is 1 matrix with the size of the whole image. And the first component captures the strongest global matrix pattern, and the next adds the strongest remaining pattern, and so on. And because these components are ordered by strength, we can stop after some k terms. In practice, we compute the SVD and choose this number, for example, k is equal to 10, and simply keep the first k columns of U matrix, first k singular values, and first k rows of V matrix. So that's how it looks like. We have some original image left, and now we kept only the first component. It looks like that. So that's our strongest matrix pattern. And after that, we are adding another strongest remaining patterns. So it looks like that. But what is compression? So we know that the whole matrix has a shape of height times width, and for the image with height 300 and width 450, we have 135,000 numbers. But when we keep only 10 components, then after this truncation, matrix U has shape of height times k. So it's h times k, the first term, plus from the matrix sigma, we store only the k diagonal singular values, so it's just plus k, and plus k times width from the Z matrix. And when we substitute, we can see that after this truncation, we have only 8,000 numbers instead of 135,000. one thing to be careful about, it doesn't change the data matrix, so it still has the same shape and number of pixels. But SVD representation returns three matrices, and we need to store and transmit only them. So the actual compressed representation is there's three matrices which contains much less numbers. And you can store and transmit those smaller matrices, and then on the receiving side, we can start it back to the original image.